We never should have landed a man on. Should have landed a man on the moon. It's a mistake. Now everything is compared to that one accomplishment. Now we go, I can't believe they can land a man on the moon and taste my coffee. I think we all would have been a lot happier if we hadn't landed a man on the moon. Then we go, they can't make a prescription bottle top that's easy to open. I'm not surprised they couldn't land a man on the moon. Things make perfect sense to me now. Neil Armstrong should have said, that's one small step for man, one giant leap for every whining, complaining SOB on the face of the earth.
If you enjoy Astronomy FM radio, please let us know with a small donation. We do rely on your support, and it's true. Every little bit counts.
AFM. You are listening to a universe of possibilities. This is Astronomy FM.
Coming up next, an Astronomy.fm original program. It's time for York Universe, a co-production of the Observatory of York University, Toronto, and the Voice of Astronomy. AFM Radio, AFM Radio, AFM Radio, AFM Radio.
Good evening, everybody. Welcome to York Universe, the astronomy and astrophysics program written and produced by the students, faculty, alumni, and darn good friends of York University. I'll be one of your two hosts for this evening. My name is Paul Delaney, and I'm joined by our good friend, the Doctor.
Hi there, everyone. Dr. John's back here tonight again, in the third person, apparently.
I can't keep him away. What can I say? We are broadcasting live from the York University Astronomical Observatory located in Toronto, Ontario, Canada. And of course, tonight, Monday night, is Astronomy Night in Canada, where the lineup is entirely Canadian, starting with ourselves, York Universe, wandering on into Western worlds, charging across to astronomy cast, quirks and quarks, not to mention science for the people. York Universe broadcasts every Monday night at 9 o'clock local time. Now that, of course, is Eastern Daylight Time here in North America. That is Tuesday morning, 1 a.m. Universal Coordinated Time. The York Universe production works in concert with our online public viewing experience. Hi, Will. Hi, Siren. They are part of the Observatory team. It runs between, at this time of the year, 9 and 10:30 here local time. Please, by all means, find your favorite web browser and point it to astronomy.blog.yorku.ca, or if you like, observatory.info. .yorku.ca. Either of those will get you to the chat room. Have a look at the pods with lots of past images. It's cloudy here in Toronto. Oh, sadly no rain, but it is very cloudy, so there won't be any live images tonight. But join the chat room, ask questions, and if you stump the team there, we will bail them out. Well, John will bail them out after I read it, of course. Our broadcast is powered by and is in partnership with Astronomy.fm, the voice of astronomy. That's capital V, capital A, by the way. For any questions or comments that you have on our past shows, or if you've got suggestions for future topics, please send us an email, observe@yorku.ca, or follow us on Twitter, which is @YorkUniverse. Okay, right, I think that's all the preliminaries. How's life, John?
Oh, life is good here, and I don't know about our audience, but I can hear those capital letters. By the way.
Well, they call that emphasis, right? You know, we're just trying to push it along there quite merrily.
Indeed.
Yes, there's lots of chat in the chat room, which is very good indeed. Lots of nice images there. I like summer observing, apart from the fact that obviously you don't get so cold. Wonderful images like the Ring Nebula. It's really, really nice to have your eye to the eyepiece at this time of the year. And one of your favorite planets, of course, is up there, John. Oh, now, come on. Your favorite planet. It's got to be Mars, right?
Yeah, it would have to be, although these days, I must admit, I'm getting around a bit more.
Well, that's true. You've been there, done that. But I always think of Dr. John and Mars almost in the same sentence. And Mars is remaining in a really nice position for observing at the moment.
It's true. It's an interesting place to be, and lots of great stuff out there. I mean, I had the wonderful experience being up in Mount Forest, where it's a little bit darker. They have a little more than our classic 6 stars in the sky that we get here in Toronto. and just a fantastic experience being shown around by the real experts out there.
Yes, you are, of course, referring to Starfest. We had a good summation of the exploits of everybody there last Monday night. Richard Block was with us and gave us the rundown on all of the different presentations. You were presenting on what?
I was talking a little bit about how we can use our own solar system to be kind of a Rosetta Stone for the galaxy at large and all of the different planets that we see out there.
There you go. Well, that sums it up pretty darn well when you think about it. The Rosetta Stone in history here gave light to all sorts of aspects of, other languages that we had yet to decipher, and all of a sudden the Rosetta Stone was wonderful in terms of turning the pages of history. Our solar system is often held up as, if we can understand what's happening here, then it becomes the wonderful template for elsewhere.
Indeed, indeed. And one of my favorite things about this is even the images that we have of exoplanets aren't really images. They're artist renderings. And where do the artists get their inspiration? Well, right here at home, looking at our own collection of planets.
Quite true. Yeah, that's something which actually a lot of the news media don't always clue into. The artists' renditions of the Tatooine planets and the water worlds and so on and so forth. They're beautiful images, and from the point of view of science fiction, I love them. I know that it's science fiction, not science fact, but the media grabs a hold of them, unfortunately, and often thinks that that's what the Hubble telescope, or pick your favorite telescope, has actually imaged, and that is not the case. They get always a little bit sorrowful when I have to point that out to them.
It is a little unfortunate, and one of the fun things, often, and you've seen some of the talks I've given, I talk about the era before we sent out spacecraft and the views we had from telescopes. Well, for exoplanets, it's not even that good. It's more like the view that Tycho Brahe had, that naked eye observing. Points of light, and
that's right.
More.
Yeah, it sums it up very well. That will change. It's not going to change in a hurry, but it will change in hopefully not too many distant decades. I'd like to be able to see some of these exoplanets up close and personal before I pass on. Fingers crossed. Fingers crossed.
Indeed, indeed.
All right, we should move along here. This week in space and astronomy history, and I'll start off the charge here, and I'm going to start talking about one of your favorite planets. So, Viking 1, both the orbiter and lander combination, was launched on August 20th, 1975. Hard to believe we're talking 41 years ago. Arriving at Mars orbit in June 19th to be specific, 1976. Now, the lander portion of this was a 572 kilogram vehicle, which is, not a bad size. Arrived at the surface July 20th, and it continued to operate until November 13th, 1982. So that's over 4 years of continuous operation. And unfortunately, we will have to admit that it would have continued longer if not for the fact that we actually overwrote where Earth was. One of the software updates overwrote the memory portion that said where the antenna needed to point, and we lost communication with it in November of 1982. So unfortunately, that was a little bit of operator error. But that,
in fact, it might still be operating.
It does have a nuclear power generator.
That's right. That's right. But if you don't know where to point your antennae, bit of a problem. Anyway, that was a 6-year, or close enough to 6 years of continuous operation, and that was a record that was only eclipsed by the rover Opportunity. Of course, Opportunity's been on the surface now for 12 years and counting. So, it is well and truly eclipsed the Viking Lander 1. But up until Opportunity, Viking Lander 1 held the record for the longest continuous operation of a vehicle on the surface of Mars. Apart from the first images that were transmitted back from the surface and the continuous transmission of that data for, as we've just said, 6 years, it conducted the first set of biology experiments that remain somewhat controversial to this day. There is still, in general terms, the expectation that what they detected was chemistry rather than biology. Every now and again you see an article, John, that suggests that maybe, just maybe, there was a little more biology mixed in there than people were prepared to believe in the 1970s and 80s.
Or even on the team itself, it's still a little bit controversial. Not everyone's convinced that it's just purely chemistry.
That's right. Not bad for a 40-year-old vehicle, a data set from a vehicle in the 1970s.
Indeed, and we're still learning new things about it. And I still see papers published every so often. And, as we learn more and more about the red planet, we go back and look at this past data in a new light. And we learn more even from, these older records.
Which just goes to show you that the data that we accumulate really continues to tell stories long after it's been collected. We're talking here specifically about Viking 1 and the data from the surface of Mars, but moon rocks continue to be analyzed long after the 1969 to 1972 pickup, and we're finding it continues to tell us stuff about the lunar surface, including the moisture content. I think of, and we'll be talking about this a little bit later on, all of the stellar images that have been picked up by observatories over the last 150 years, the glass plates, how they represent pieces of history that help understand the data that we collect today. So lots to be said for maintaining those data sets, keeping them safe, keeping them pristine, not just the, shall we say, the data reduced versions, but the original raw data. So you can always go back to that first principle and check things out.
Well, it's interesting in particular that you mentioned the lunar samples, of course, one of the national treasures of the United States. And we get more and more samples, and we're hopeful to get a few more samples from celestial bodies in a couple years' time. And when you collect these samples, you always set aside a certain amount for later because you know that the technology is going to get better, you're going to get new analysis techniques, and so you want to have something still left over so you can continue to learn from that.
Now, that's actually a very good point. Does that tell me, and I don't know the answer to this, but does that tell me that some of the moon rocks were deliberately set aside from the 1969-1972 for exactly that type of analysis that you're suggesting?
That's exactly right. The whole point here is that you don't want to use up all of the sample that you bring back. You have so much that you set aside for immediate analysis, and sometimes you can distribute a little bit to partner labs if there's enough material. And then there's some that you safeguard for later use once the technology improves. Now, of course, going out to a body like the moon or an asteroid to collect sample isn't the only way that we get samples of these particular rocks. We can actually get samples delivered for free through meteorites. And this is an excellent segue, I think, into our next day in history here.
Well, it certainly is, although not quite our next one, but getting there, because let me just talk about Voyager 2 for a sec. So hold that thought, okay? And then we'll move on to yours.
Well, no need to give you a break if you don't want one, Paul.
Oh, well, what a guy. All right, go for it. Tell us about that rock that we found in Antarctica.
All right. Well, it's definitely one of the most well-known, superstar of meteorites out there. You've got this rock, and it's got the, not the greatest name, kind of dry, ALH 84001. What that tells you is that it was the first rock that was found by the Antarctic Search for Meteorites in 1984 around the Allan Hills area of Antarctica. So that's, it's more of a descriptive title. But it really made a splash quite a bit later, 12 years later, on August 7th of 1996. That's when we had the announcement that rocked the planetary science world, looking into this particular bacteria or other biological filigree type of things. And, it's something that is still a little controversial as to whether that's what they are. They're definitely very, very small features, smaller than any biology that we have here on the Earth. At the same time, there is the question of, whether this is a precursor, what's going on here. So by and large, most scientists today think that this particular rock is not an example of an early Martian biology. But my oh my, back in '96, it was a huge story. And the whole renaissance of planetary science in the 1990s was really kick-started by this, along with, of course, the Pathfinder mission, back when science broke the internet.
Sums it up very well. I do remember the August of 1996 because not only was it a really important press conference that NASA, of course, was announcing, there was actually a contribution from the President of the United States. Bill Clinton made an announcement, if you will, heralding the actual press conference. Because let's face it, if this had come to be, that is to say, this was the press conference that announced the possibility of life in this meteorite and further verification had yielded a positive confirmation, then everybody wanted to be in on the act. And so the President of the United States wanted to be able to say, yeah, I was there, I led the charge, I made the announcement, et cetera, et cetera, et cetera. It has probably not come to pass in that regard, as you said, John, that most of the follow-up observations have more or less concluded that it was geology and chemistry, not biology. But that poor little meteorite, it started out about 1.93 kilograms. I think it's probably down to a few hundred grams. No, not quite, but it certainly has been analyzed to death, and as you say, really has kick-started a renaissance as far as planetary observations and astrobiology in general. You can date it all the way back to 1996.
Indeed, it's one of this sort of rare class of meteorites called the SNCs from Mars. And so, we have that nice little fingerprint within them that identifies them. The great thing about going to a place like Antarctica is that you can have all of these rocks sort of captured, and they're on that nice white background, so you can identify them reasonably easily. And they're eroding their way out. I mean, with Allan Hills, it probably fell something like 13,000 years ago. And you can go down there and get samples of it, or at least the Antarctic Search for Meteorites does this on a regular basis, which is really nice because I can tell you that buying these on the open market is not cheap.
It is not, but you're absolutely right. Science expeditions go down there every year into the southern hemisphere summer, so December, January, February, and they literally are picking up hundreds per year. The expeditions are very, very fruitful in terms of the number of meteorites they're picking up. Not all Martian meteorites, obviously, but meteorites in general. I think last I read there's something like 30 or 40 confirmed Martian meteorites that have been found to date on Earth. Do you remember the number, John?
I don't remember the specific number, but that sounds like it's in the right area.
Yeah, it's not a huge number. As I said, we find hundreds per year. We're only able to absolutely, with great certainty, determine the locations for a very small fraction of them. We can date we can confirm the Martian origins, we can confirm the lunar origins. After that, it becomes a little bit more speculative. There are various families of main-belt asteroids that we suspect have got meteorites here on Earth, but the vast majority of the meteorites we find, we really do not know their origin, but they do give us pieces of the puzzle of our early solar system and the origins, development of the solar system. The ALH 84001 is particularly helpful because it's about 4 billion years old, I think, is the current dating on it, which makes it, very, very old.
That's right. It's unique among the SNCs. In fact, it's by far and away the oldest of that. And that's sort of the crystallization age. That's when the rock formed. It's not when it was blasted off of Mars, which was something like 17 million years ago.
Indeed. Yeah, the history of these sorts of rocks is quite fascinating. My class always marvels at the fact that we can say, yes, it's been on Earth give or take 13,000 years, that it left Mars for Earth about 17 million years ago, yet the rock is 4 billion. I mean, it's, when you piece together the information, the radioactive dating for the age, the cosmic ray bombardment for its travel in interstellar space and so on, interplanetary space, it all is a wonderful, wonderful story.
It's amazing what you can tell from 1.93 kilograms of rock.
Absolutely. All right, our third and final this week in space and astronomy history is from a similar era. Voyager 2, the 825-kilogram spacecraft, was launched on August 20th, 1977, on its journey to the outer solar system, legendary journey to the outer solar system. It became the first, and at the moment to date, the only spacecraft to fly by Uranus. That was January of 86. I should actually throw this to the chat room, but somebody would Google it too darn quickly. It flew by Neptune in August of 1989, and this is all after its initial encounters with Jupiter, July of 79, and Saturn in 1981. Interestingly enough, the spacecraft continues to transmit data, and in fact, if you look on the web, you'll find that the Voyager mission is really divided up into its time hanging out in the planetary domain, that is to say Jupiter, Saturn, Uranus, and Neptune, and that time frame is, give or take a bit, 12, 13 years, and then the interstellar mission, which is the rest of its life, and that's like about 26 years at this point in time. When the mission planners were putting this whole mission together back in the early 70s, I dare say very few of them expected the spacecraft to continue to be operating successfully at 2016, but that's exactly what it is doing. The spacecraft continues to transmit data from a distance of about 112 astronomical units. That's 15.5 light hours from Earth or the Sun, close enough to being the same thing at this point. And of course, it's approaching interplanetary space. It's about to cross the heliopause. It's moving through the heliosheath as defined by its predecessor Voyager 1, which skipped through that region about 3 or 4 years ago. So Voyager 2 is trailing behind Voyager 1 because it had a few other things to do on its way out. But nonetheless, 112 astronomical units. That's a stunning distance. That's 112 times the distance the Earth is from the Sun. And as I said, this vehicle was launched August 20th, 1977, so 39 years ago. Pretty darn good for a spacecraft, John.
It's definitely managing. I mean, that's your good design. You think of opportunity as well, also vastly exceeding its design lifetime. And one thing that I always enjoy with these missions where you have more than one spacecraft is the way that you name them, the way that you number them. So I don't know if many people appreciate this, but Voyager 2 was the first launch of the Voyager spacecraft program. Yes. Voyager 1 came later. So maybe I shouldn't spoil it for those people tuning in the first week of September. But Voyager 1 was actually the second one launched. And the reason for that is that the celestial mechanics made it so that the launch in early September would get the spacecraft there to Jupiter faster. And so to avoid any confusion upon the arrival at Jupiter, it was designated that Voyager 1 would get there first, and so it had to launch second.
Celestial mechanics, ain't it grand?
And eventually Voyager 2 will pass Voyager 1 again, as it got more of those gravitational assists on its way out of the solar system. So even though Voyager 1 was the first to leave the solar system, Voyager 2 will go and overtake it once more eventually.
Again, it was really exciting times watching Voyager. Looking up the dates. We'll talk about this a little bit more next week because that's closer to the anniversary of the flyby of Neptune. But being able to arrange for the data to actually make it back to the Earth for the flyby of Uranus and then Neptune, those distances for the Voyager spacecraft when the Voyagers were launched were actually beyond the capability of the Deep Space Network. So, the spacecraft, once it's launched, has got its power already defined, so the transmitter has only a certain amount of capability. What we had to do, of course, was proceed ahead and upgrade the deep space network here so we could actually listen to all that wonderful data that was being picked up by the spacecraft. It was a really exciting time in that sense.
It's always a good argument for your funding agency. I have a spacecraft on the way to Uranus and no way to listen to it. Please help.
Oh, you're a cynic, Dr. John. You're a cynic.
And something well, on the positive side, if I can go and talk about something that is really fantastic. I mean, the opportunity to do the grand tour, to visit each one of the outer planets in order, only comes around about once every 176 odd years or so, give or take 10 or 20 years.
Saturn, Mars, and then always an excellent sight. Mars, we're well past opposition for both the planets these days, but if you've got a small telescope, Mars and Saturn are well worth seeing. And if you hang out till midnight or thereabouts, you can swing your scope across. You will now need star charts or setting circles, but Neptune and then Uranus are both rising, so it's not too bad a time to catch all of the planets. Venus is sneaking into our evening sky. It's still very low at the moment in the west. Jupiter, Saturn, Mars, and then if you're just a little patient, waiting for the latter part of the evening, Uranus and Neptune. So it's a good planetary time of the year, John.
Well, for me, all times of the year are good planetary times.
Yes, what can I say? If you were up late on Saturday night was Sunday morning, everybody will know that SpaceX has done it again. They launched a Japanese communications satellite into orbit and then promptly brought their first stage of their Falcon 9 back to the floating platform in the Atlantic. What's the name of that floating platform? Of course, I Still Love You. I love the name. At any rate, this is the 6th successful landing, the 4th at sea for the SpaceX company. They've nailed both of their landings, their land landings back at Cape Canaveral. They've now put 4 successfully down on the barge at sea, so 6 altogether, and one of those has been brought back and has now been test fired, I believe, about 4 times for 2.5 minutes each. So they're beginning to really gather some serious data with respect to the performance of these vehicles after return. I have not heard of a date yet for when they are planning to try and redeploy to deploy a satellite with a redeployed first stage. And obviously SpaceX is very, very happy with their ability to bring their assets back to ground safely.
Well, certainly it's something that, it's nice to be able to reuse as it brings down the cost of access to space. But I can understand the trepidation of those people putting payload on the top of the rocket. Who wants to go first with the reused ones?
I dare say there will be a significant discount, shall we say, for that first customer.
Or maybe they've got another wheel of cheese to send to orbit.
True enough. It's very impressive, however, to see SpaceX operating so successfully at this point in time. Okay, enough of these little tidbits in passing. Time for a little bit of news. We've got a few articles here. For those of you who were with us last week, you will recall that our last full article that we were chatting about was dark matter, how a lot of the current searches are coming up empty. We were talking about the LUX observations. That's the underground xenon detector that was trying to find evidence for a dark matter particle, and it was unsuccessful over the last couple of years' worth of data collection now. But we finished that article, and I was about to plow onto another dark energy search, which is underway. And, of course, we ran out of time. So, dark energy, and this is part 2 of the conversation that we were having last week. Dark energy, of course, is the name that we give to the unknown cause of observations that suggest that the universe's expansion is accelerating. I mean, we know we live in an expanding universe, but back now nearly 20 years ago, we suddenly realized that expansion rate was accelerating, not deaccelerating as we were sort of expecting, courtesy of matter and gravity. But what's causing that rate of acceleration? And, of course, we don't know the answer to that. There are some theories as to what may be the cause, but none have given scientists any great confidence that the mystery is on its way. Courtesy of matter and gravity. But what's causing that rate of acceleration? And, of course, we don't know the answer to that. There are some theories as to what may be the cause, but none have given scientists any great confidence that the mystery is on its way to being solved. However, progress is underway in trying to figure out what is dark energy. And the latest tool, if you will, has been delivered by hundreds of astronomers from the Sloan Digital Sky Survey, that's the SDSS, the Max Planck Institute for Astronomy and Astrophysics over there in Germany. They have put together a map of 1.2 million galaxies. I'm going to say that again. They've put together a map of 1.2 million galaxies, spanning a volume in space of 650 cubic billion light years. That's a lot of space. The largest map of galaxies ever compiled, or at least yet compiled. Okay, so why are they putting together so many galaxies? Well, over a decade, and it took them that long to put all of the measurements in place, then that's what's embedded in this map, it is allowing scientists to probe the nature of the expansion of the universe over not just a very large region in space, but also over a very long time scale, okay? Because remember, we are looking deeper into space. It's not just the volume, but it's also the time that is associated with the volume. This is because the baryonic oscillations, it's called the baryonic, I'll try that again. It is called the Baryon Oscillation Spectroscopic Survey, BOSS for short, okay? And it's part of, as I said, the Sloan Digital Sky Survey. They are generating really precise measurements. By studying the tug between dark energy and dark matter, so dark matter and regular matter that we see, baryonic matter, that represents the gravitational signature associated with galaxies. And so that
signature is embodied by the galaxies. But by measuring how the galaxies are moving with respect to each other, they can actually measure how much is the dark matter tug, the gravitational tug, is being overcome by the expansion rate. The scientists were able to determine thus the baryonic acoustic oscillation. So this is the measure that they use to try and determine how much the expansion of the universe is overcoming the gravitational tug that brings material back together. So the map of the 1.2 million galaxies allows them to measure this baryonic acoustic oscillation, and therefore they can actually measure the expansion rate of the universe over and above what we're seeing with respect to the gravitational tug that's keeping the galaxy groups together. Using only the observational data and imposing no theoretical assumptions, the results so far have shown that there is, in fact, this unaccounted for effect driving the expansion of the universe. That is to say, dark energy does exist, and that the numerical values found so far are really very, very accurate. So the measurements are really accurate, sort of within plus or minus 5%, saying that, in short, using the BAO, the baryonic acoustic oscillations, across some 7 billion years of time, that's in this 650 cubic billion light year volume in space, that the time that we're seeing that the expansion of the universe is being driven by something. And that something, of course, we have dubbed dark energy. So, bottom line to all this, we really do see an acceleration in the expansion rate, that it is driving the galaxies further and further apart in a way that is accounted for by the notion of dark energy. So unlike dark matter, where we haven't yet found that darn elusive particle, we are seeing evidence from the galaxy distributions for dark energy. Very, very interesting times that we live in, John. Well and truly beyond the solar system.
Indeed, going off to the furthest stretches, the furthest reaches of space and time, as it were.
Absolutely, absolutely. And of course, the Sloan Digital Sky Survey is just continuing to expand its map. So we've got 1.2 million now. They are going to continue this process, looking for ever greater detail for the BAO over a longer time scale, and hopefully they'll be able to further quantify the notion of dark energy. And of course, there's lots of people out there who are building the theories into, how it came into existence at the Big Bang, but that's all well and truly above my pay scale. I do not understand some of those theories. It's as simple as that.
Well, this is definitely one of those these interesting projects, that are going out there and gathering a lot of data to be sifted through and cut in various different ways by scientists and really anybody who's interested in what's going on. And what's coming out of it reminds me of our own spacecraft missions that we send out into the solar system, that you collect that bunch of data, and maybe years later that you look at it in a new light and you find something you never thought you would.
Absolutely. It's really, really interesting stuff, even if it is drenched in mathematics, but it does talk to us about the way our universe is expanding.
Indeed. Well, if I can, I will bring the discussion back to our backyard, practically, inside our own celestial house.
Sounds fine.
Talk about my, as you mentioned earlier, my favorite planet. Time to play favorites. And that would be Mars. And of course, when you're talking about Mars, you just can't avoid water. It seems like every year there's a new story about water on Mars, despite the original discovery in the polar caps back in the 1960s. But that's just because water is such an interesting thing. Often when we go to Mars, we're following the water.
unaccounted for effect driving the expansion of the universe. That is to say, dark energy does exist, and that the numerical values found so far are really very, very accurate. So the measurements are really accurate, sort of within plus or minus 5%, saying that, in short, using the BAO, the baryonic acoustic oscillations, across some 7 billion years of time, that's in this 650 cubic billion light year volume in space, that the time that we're seeing that the expansion of the universe is being driven by something. And that something, of course, we have dubbed dark energy. So, bottom line to all this, we really do see an acceleration in the expansion rate, that it is driving the galaxies further and further apart in a way that is accounted for by the notion of dark energy. So unlike dark matter, where we haven't yet found that darn elusive particle, we are seeing evidence from the galaxy distributions for dark energy. Very, very interesting times that we live in, John. Well and truly beyond the solar system.
Indeed, going off to the furthest stretches, the furthest reaches of space and time, as it were.
Absolutely. Absolutely. And of course, the Sloan Digital Sky Survey is just continuing to expand its map. So we've got 1.2 million now. They are going to continue this process, looking for ever greater detail for the BAO over a longer time scale. And hopefully they'll be able to further quantify the notion of dark energy. And of course, there's lots of people out there who are building the theories into, how it came into existence at the Big Bang, but that's all well and truly above my pay scale. I do not understand some of those theories. It's as simple as that.
Well, this is definitely one of those these interesting projects, that are going out there and gathering a lot of data to be sifted through and cut in various different ways by scientists and really anybody who's interested in what's going on. And what's coming out of it reminds me of our own spacecraft missions that we send out into the solar system. That you collect that bunch of data, and maybe years later that you look at it in a new light and you find something you never thought you would.
Absolutely. It's really, really interesting stuff, even if it is drenched in mathematics, but it does talk to us about the way our universe is expanding.
Indeed. Well, if I will bring the discussion back to our backyard, practically, inside our own celestial house.
Sounds fine.
Talk about my, as you mentioned earlier, my favorite planet, if I'm to play favorites, and that would be Mars. And of course, when you're talking about Mars, you just can't avoid water. It seems like every year there's a new story about water on Mars, despite the original discovery in the polar caps back in the 1960s. But that's just because water is such an interesting thing. Often when we go to Mars, we're following the water. Water has this lovely association with habitability, with life. And one of the most exciting water discoveries that we've seen in the last decade came about 6 years ago with a team at the University of Arizona, led by Alfred McEwen, using the HiRISE camera, which is run out of the U of A. And they happened to note that on different slopes, what you would get is this seasonal recurrence of dark streaks, these recurring slope linea, they called it. In some ways, the blandest possible name, but they really hinted at something else. So the recurring slope linea, the RSLs, we always suspected that it was water that was going on, that was driving these features. And in fact, last year, we put the final nail in the coffin there. And what do we see? Lots of salts. This is something that was a really exciting, big announcement by NASA last September, actually, that we saw that salt, that briny water flowing out onto the surface. Now, as I mentioned, this debate about the possibility of water on Mars, it's almost as old as our exploration of Mars itself. It goes all the way back to our earliest spacecraft. And really, apart from the obvious shaping of the planetary surface, the existence of water within easy reach of any future human explorers or settlers is indeed very promising news for those people who are thinking along those lines eventually. There is an additional little wrinkle, though, that's sort of come into this lovely story about having these little lineae, having these little dark streaks caused by water gushing out of the inside of the planet, out of aquifers. And that comes from some research led by Matthew Chodnacki, also from the University of Arizona, my alma mater. And what they're suggesting
then that's what's embedded in this map. It is
there, and what do we see? Lots of salts. This is something that was really exciting, a big announcement by NASA last September, actually, that we saw that salt, that briny water flowing out onto the surface. Now, as I mentioned, this debate about the possibility of water on Mars, it's almost as old as our exploration of Mars itself. It goes all the way back to our earliest spacecraft. And really, apart from the obvious shaping of the planetary surface, the existence of water within easy reach of any future human explorers or settlers is indeed very promising news for those people who are thinking along those lines eventually. There is an additional little wrinkle, though, that sort of come into this lovely story about having these little lineae, having these little dark streaks caused by water gushing out of the inside of the planet, out of aquifers. And that comes from some research led by Matthew Chodnacki, also from the University of Arizona, my alma mater. And what they're suggesting is we may need to rethink exactly what the origin of this briny water is. They don't contest that briny water is what creates these RSLs. What they suggest is that it might not be coming from aquifers on the inside. What gives them that sort of hint that it might not be from aquifers themselves is the fact that when they look for these RSLs, they find them all over the place. They find them in places where aquifers cannot possibly be, like mountaintops, for instance. And the area that they looked at all throughout Valles Marineris, they found things pretty much wherever they looked. So now the question is, where does that water come from? And there is a process that'll do it. It's something that we call deliquescence. So anybody who has tried to clear a snowy driveway in the wintertime will recognize the power of salt. Even just regular sodium chloride salt, it changes that freezing point of water and moves it from 0 degrees Celsius, 32 Fahrenheit for those of you in the United States, all the way down to minus 22 Celsius. That is the lowest temperature at which your lovely salt mixture can stay nice and briny. And in fact, with a really, really strong salt, like the perchlorate salts that we saw at the Phoenix landing site, you can get water all the way down to something like minus 68 for very specialized salts to the minus 70s. These salts love water so much that they can pull it directly from the atmosphere until they create a brine for themselves. And maybe that's what's going on here, is that the water in the atmosphere is getting caught up in these salty brines. And so wherever there's enough water in the atmosphere, wherever there is enough of this salt, you get this liquid, and then it just proceeds downhill. Now, we had thought there wasn't quite enough water vapor in the Martian atmosphere to really drive this process. So if this is indeed what's happening, it suggests that there might be more than we had anticipated. However, I will point out that Valles Marineris is one of these places on equatorial Mars where we see a lot of early morning fog, and we see that in a number of the craters and topographic lows as well. So it could be a case where the water vapor is just recycling, because Valles Marineris is quite a deep feature on Mars. It has its own circulations. So really, this one is not yet decided. The debate here, clearly not yet over, but either way, it's just getting more interesting.
I would never have thought that there was enough water vapor in the Martian atmosphere. All of my readings had suggested that there just wasn't very much there at all. But with this research, the suggestion, as you say, is that there may well be enough to generate that absorption process, that deliquescence, and instead of the hoped for aquifers full of water that are just waiting for us to tap into, we may have to sort of try and distill some of that water from the atmosphere. That's not nearly as helpful a process for the Martian colonists, shall we say?
Well, we are spoiled here on Earth. We definitely have very good proven water reserves as compared to many other planets, at least in the inner solar system.
Yeah, quite true. We've got more water than we can shake a stick at in most places, although as I said to you at the beginning of the show, off air, I really would like a little more water for my garden here, but that's just a local affair. So these RSLs, the story is, the jury is still out whether or not it is water from beneath the ground, water from the atmosphere, or perhaps indeed a combination of both. Do we know, John, whether or not there is any additional insights that, for example, Curiosity is going to be able to provide for this process to solve this dilemma?
It's possible, although the interesting thing with Curiosity is that we are in an abnormal place. Just about every deep crater in equatorial Mars shows fogs in the early morning. This is something that has been seen by the ExoMars orbiter. It's on that very long loopy orbit, and so it gets to see things on Mars at unusual times of the day, different from a mapping orbiter. The one place where they've never seen any of these fogs, any of these clouds, is Gale. And with our own instrumentation, it seems like Gale is a pretty darn dry place. If you think of the Atacama as the driest place on the Earth, well, Gale Crater, where Curiosity is the Atacama of Mars.
Yet we went there because of its past history of water, as I recall.
That's right. Going from lakes to now this Atacama of Mars.
The entire Earth history by only, say, visiting the Great Canadian Shield. If you did that, you would certainly not be able to piece together the entire history of our
how much light is blocked is typically a few percent at best, often considerably less than that. But it's regular as clockwork if it's a planet that's orbiting that star. Tabby's star, however, yields brightness variations that exceeded over 20% of the dimming of the starlight, and it did that over timescales irregularly measured in days, not hours, in days. This, needless to say, really did perplex everybody, scratching of the head and so on. Having exhausted all of the usual explanations, the best astronomers could come up with is that we were looking at a swarm, I'm not sure if that's the right term, but a swarm of comets disintegrating a la Schumacher-Levy 9. Remember that comet that sort of flew in a little bit too close to Jupiter back in 1992 and then came back and socked Jupiter? Explanation, but it was the best one that we came up with. So we went ahead and sort of looked at it and looked at it and looked at it, and we concluded that, well, we really didn't believe it. So what do we do when we don't understand those sorts of things? Well, we revert to alien megastructures. Well, that wasn't a very satisfying explanation, although it was very exciting, but it really wasn't very satisfying. Call went out for more data, and so astronomers started digging into the archives, into the history of any observations of Tabby Star to see what trends may have existed. So basically supplementing Kepler's data. And then we actually went back into the Kepler data set itself, because Kepler's data was being used primarily to look for transiting exoplanets. We'd never really looked hard at the long-term trends. If there was a variable star in the Kepler data set, that's fine, varying on timescales of hours or days, but we weren't really looking at things that had timescales of months to years. So they started doing that. Okay, well, it's a longer story, but let's just cut to the chase here. It appears that Tabby Star is indeed fading. Brad Schaefer from Louisiana University sifted through the history plates at the Harvard College Observatory, basically 100 years of glass plates, and concluded that the star was fading by as much as 0.16 magnitudes per century. Putting that out there in the public domain, there was a little bit of yelling and screaming, astronomically speaking, in the literature. But the conclusion was that the star did seem to be fading. Well, two other guys, Manette and Simon, suggested from the Kepler data set itself that the rate of fading of Tabby Star was in fact twice that rate in the first 3 years of the Kepler data set, and then increased dramatically, like several-fold, in the last year of the data set. So, unfortunately, of course, we're no longer looking at Tabby Star, so we can't interpret any more data from the Kepler data set. But over the 4 years that we were able to observe Tabby Star, there certainly did appear to be a significant dimming in support of Schaefer's historical analysis. What does that mean? Well, that's a darn good question. We're really not sure what it means, but it certainly does say to us that Tabby Star has got a really rich history and that it deserves a lot more analysis. And so the word is out there. People are observing this star now. Of course, we've had the SETI people listening in on Tabby Star. Nothing to report as far as ET is concerned, but the mystery surrounding both Tabby Star as well as the light variations that we've been detecting with Kepler remains. Stay tuned for further information. Definitely a little bit of mystery here, John.
Oh, without a doubt. I mean, 20%, we could see that easily with the 40 centimeter. Heck, we could probably see that with the 4 centimeter I just have.
That's true. Surprised that of all of the stars that Kepler was observing, 150,000 of them, roughly speaking, if memory serves, that we only found really one really bizarre star, and that's Tabby Star.
Well, a good question. What is the fraction of bizarre stars in the galaxy?
Well, therein lies a good point. Don't know is the answer to that. But, obviously the more we dive into this data set from Kepler, the more interesting things we are going to find.
Indeed.
Okay, folks, we're at the top of the hour. Sorry about your Titan-flooded canyons there, John. We'll have to talk about that next week. But you've been listening to York Universe. Find.
Indeed.
Okay, folks, we're at the top of the hour. Sorry about your Titan-flooded canyons there, John. We'll have to talk about that next week. But you've been listening to York Universe, folks, the astronomy and astrophysics program brought to you by the York University Astronomical Observatory. Very many thanks to the chat room crowd there at observatory.info.yorku.ca, keeping the observatory team on their toes despite the cloudy skies. Please stay tuned because, of course, we've got lots more astronomy coming your way. Western world, science for the people, quirks and quarks. This is Astronomy Night in Canada, so please do stay tuned. But for the time being, from myself, Paul, I'm going to wish you all a great week, and we'll be back same time next week. So good night from me.
And good night from me.
We hope that you've enjoyed this program from AFM Radio, the broadcast service of Astronomy.fm. This program has been released under Creative Commons license. Please contact us for details. You may find more of our AFM original programs on our website. It's really easy to find us. We are Astronomy.fm. You may also find us in the iTunes radio listings near the top of the News Talk, and also